Okay, IB. Our next section, our next video is on exponential graphs, transformations, and logarithms, which I'm going to cover as quickly as possible. It's quite a mouthful, but we're just going to look at the basics. So firstly, let's have a look at an exponential curve. Now, an exponential curve is a curve that of the form y equals a to the power of x, where a is a constant. So if we have a look at a being a positive number, let's say, for instance, our example first might be y equals 2 to the power of x, and have a look at what that curve is. Look at some key points. When x is 0, y is equal to 2 to the 0, which is 1, so that would be there. When x is 1, y is 2 to the power of 1, which is 2. When x is 2, y is equal to 3, 4, 5, 6, 7, 8, and we can soon see that we're the curve is growing in what's called an exponential fashion. Now, what happens to negative x? Well, 2 to the minus 1, well, that's a half. So minus 1 goes to a half, 2 to the minus 2 is like a quarter, 2 to the minus 2 is an eighth, and we're getting very tight to the line there. And we've got a curve that looks a little bit like that. The x-axis acts as an asymptote, and this is y equals 2 to the power of x. Now, what would happen as 2 changed? Well, the value of 2, if the value of 2 changed and became larger, then this would, the effect would be a vertical stretch, and this would get tighter against the y-axis here. If we add or subtract the value on the end here, if we wanted to add 2, then this would shift the whole exponential curve would go up 2. So it wouldn't go through 1 anymore, it would go up through 3. If it was minus 2, it would come down 2. So that would be the transformation. Now, I'm talking very quickly and generally about transformations. It might be a good idea to, I'm just trying to erase now my arrows, it might be a good idea to observe on page 113 the notes there. So refer to page 113 for notes on graphical transformations, because they will affect our exponential curves as they'll affect anything. But just in general, adding or subtracting, that shoves up or down. If we adjust in here, so let's say we put a little minus 2 in there, then that would be a horizontal adjustment. So that would shoot our exponential curve off to the left or right. So in this case, for the minus 2, it would shoot it off to the right. If it was plus 2, it would shoot it off to the left. It would just shift the whole curve. It would just be like picking it up and moving it horizontally. Remember, if the numbers are added to the end, then it's a vertical shift up and down. Okay, so that deals with that. If we looked at changing the value of 2, so we looked at multiplying by a, let's say multiplying by p, for instance, then if you multiply a function's values by p, then what that results in, as I mentioned earlier, there will be a vertical stretch. So it would be like stretching the curve, and it would tighten up against there and in against here, and it would just tighten the whole thing up. It would be like, it's what's called a vertical stretch. If we put that p in up against the x-axis, against in here, so it became px in there, then that's what's called a horizontal stretch, and the factor would be 1 over p. So that would be a horizontal stretch of 1 over p. In this case, it would be like a horizontal compression, which would have the similar effect to the vertical stretch we looked at there a moment ago. But as I said, refer to page 113 for the general rules on transformations of graphs. Now, if we go back to, just one other thing we could look at there, and that is what happens when we put a minus x out the front. Well, a minus x will flip in the y-axis, so that will flip it like so. So this would be 2 to the minus x. If this is 2 to the x, y equals. That will be a reflection y-axis. If that minus comes down to, if it comes in front of the 2, so let's just try and erase that. and put that minus now in front of the 2, so it's minus 2 to the power of x, well that would be a reflection in the x-axis of 2 to the x. So that would be like so, y equals minus 2 to the power of x. So we've got some transformations there of our exponential curves, and hopefully we've got a little hang on that. Now let's, I want to have a look at logarithms and just some introductory notes on logarithms. Now logarithms are an examination or a study of indices, essentially. A study of indices. And the best way of starting off here is to explain that that because 2 cubed is equal to 8, log base 2 of 8 is equal to 3. These two statements here are exactly the same. This logarithm statement, which is new to you, this is certainly not new to you, 2 cubed equals 8, but the logarithm statement here, this is base 2, so we call this, that's the base there. So you can see the base 2 there lines up with the base 2 there. The index ends up over there, so that is, as you can see, the subject of a logarithm, or the focus of a logarithm is the index. So the log of 2, so log of, the way you'd read this would be the log of the, put this in quotation, the log, come on, I can do better than that. The log of the logarithm of 8 to base 2 equals 3. That is how you would read that. The logarithm of 8 to base 2 equals 3. So if we have a look at another example, what is the logarithm of 16 to base 4? Well, what this is asking is, what do you raise 4 to get 16? Well, the result is 2. So if you look at it like this, it's 4 to the power of that equals that. And always with a logarithm, that's how you can sort of unlog it. You can take the logs out. So you could take out of that, you could say, oh well, as written without the log, that's 4 to this power here is equal to 16. Okay, some more examples. Let's say that we wanted to know, let's say log of is equal to, so the log of a fifth to base 5, well, that's equal to minus 1, because 5 to the minus 1 is equal to 1/5. The log of, have a look at another example here. Let's say we're looking to solve log of x to base 16 is equal to a half. So what that says, and this is how we look at solving it, that says, okay, well let's take the log out of it. 16 to the power of a half is equal to x. So therefore, x is equal to the square root of 16, and x is equal to 4. So we're solving logarithmic equations now all of a sudden, just through our knowledge of what a log means. It means this base to this power is equal to this. This is the result. This is the result. The x is a result of raising 16 to the power of a half. Just like a fifth is a result of raising 5 to the power of minus 1. 16 is a result of 4 to the power of 2. I think you get me. Just looking at a couple of other examples before we finish up on this video. If we had a look at what is the result of log 1 to base 4. Well, so 4 to the power of what gives us 1? Well, that's 0, isn't it? So in fact, could we generalise here? That's saying, well, that 4 to the 0 equals 1. Could we generalise and say that log of any base, so log of 1 to any base will be equal to 0, since a to the 0 is equal to 1. Well, that is correct. So we could say that, and we will do so. What else can we say? Well, log, let's use 4 as our base again. What's log of 4 to base 4? Oh, 4 there, well, yeah, that's 1, isn't it? Hopefully you're getting the answers before I'm writing them down. 4 to the power of 1 equals 4. Could we therefore get ahead of the game here and say, well, come on, let's generalise here, that log of a to base a is going to be equal to 1. There's a nice little result there. Have a little think about one other thing for me. Can you take the logarithm of a negative number to any base there? Can that be worked out? And that's one perhaps for you to feed back tomorrow in class. Let me know your thoughts on that. We're ready now to tackle some exercises on logarithms and also some exponential graphs. See you tomorrow.